Good morning, everybody. Welcome to this presentation. It's a great pleasure for me to introduce the dissertation for Stefan Haller. His thesis is called Towards Low Voltage, High Current, a Pioneering Concept for Battery Electric Vehicles. My name is Kent Bertilsson. I will be sharing this dissertation. I have been Stefan's supervisor for the last 2 years. But I have had the opportunity to work with Stefan for quite much longer time than that, already from the master level. He was here at the Munich University. Addition to me, I will also acknowledge Professor Bengt Oelmann, who has been his thesis or his supervisor until his licentiate thesis, and also Dr. Peng Cheng, who have to large extent initiated the work that Stefan have been working on. So then with us today we have 4 prominent persons who are doing the evaluation of the thesis and the work and the presentation. So first of all, it's the opponent. It's Professor Dr. Engineer Dieter Gerling from Bundeswehr University of Munich. He have a very long track record in electric drivetrains from Bosch, and also co-founder of Volabo, who is a company that is pioneering low voltage drivetrains for electric vehicles. In the grading committee, we have Professor Yujing. He's a head of electrical machines and power electronics at Chalmers. He's also been active at ABB for many years. We also have Professor Alaküla. He's a specialist in electric power engineering and electrical drivetrains. He's active in Lund University and have been a long track record also from Volvo. And then we have Associate Professor Göran Thungström from Munich University. He's specialized in semiconductor devices, manufacturing, characterization, with special focus on detector applications. So I will first start with the schedule for this presentation. So the first thing that will happen after this I present the schedule is that the opponent, Dr. or Professor Dieter Gerling, will present a short introduction placing the thesis into context. Then Stefan will present his work with a PowerPoint for about 30 to 40 minutes. After the presentation, we'll have a short technical break for 5 to 10 minutes. Then that will also stop the YouTube broadcast for this presentation. After the short break, the word will be handed to the opponent, and he will lead the discussion together with the respondent. When the opponent is satisfied with the discussion, the word is handed to the grading committee, and they will have the opportunity to ask a few questions that they still would like to have some answers to. Then after the opponent and grading committee are satisfied, then the general audience here and in the Zoom meeting will have the possibility to ask some questions also. So after this questioning, there will be a longer break, somewhere 20 to 30 minutes. And there you are encouraged to stay in the Zoom meeting and chat and mingle. And during this time, the grading committee, we will meet in a separate room, and they will discuss the thesis and the presentation. So after this meeting, the grading committee will return to the Zoom meeting, and they will deliver the final decision to the respondent. If the decision is positive, and the respondent pass, then we'll have opportunity to congratulate Stefan. And it's impossible to say how long the whole event will take, but normally the procedure is less than 3 hours. So, first of all, I would like to introduce the opponent, Dieter Gerling, that will place the work into context.
Okay, so thank you very much. Yeah, I'd like to introduce the work of Stefan Haller shortly. Well, he deals with the topic of low voltage drivetrains for electric vehicles, and as we all know, electric vehicles reduce the dependency from fossil fuels, and they reduce the amount of pollution, at least locally, but even globally, at least to my point of view. And so therefore, these vehicles are one step towards the reduction of global warming. Currently, nearly all electric cars that you can see on the road have a battery voltage of about 350 to 400 volts. And one main reason for this is that especially the power electronics could then be taken from the industrial applications and therefore reduce the development complexity. However, there is very much the question if different voltage levels are more advantageous than the one chosen so far. So this question has been dealt with by Stefan Haller, as he has investigated much lower voltage levels down to 48 volts. And he worked on this topic not only for the machine, but for the entire drivetrain of an electrically driven vehicle from the electrical machine via the power electronics till the battery. Of course, if you have a certain power demand for such a vehicle, low battery voltages means that you have quite high battery currents. And very often I'm hearing that high currents are directly linked to high losses. But this is not necessarily directly linked. So there are possibilities to reduce the losses. And well, I think that we will learn much about low voltage drivetrains during this public defense seminar. And I would like to hand over to Stefan Haller to give his presentation.
Thank you very much, Professor Gerling. I hope everyone can hear me quite well. So I try to get the screen sharing running here. So, all right. Welcome everybody to my PhD defense titled Towards Low Voltage High Current, a pioneering drive concept for battery electric vehicles. Before I actually start, I'd like to present the errata. There's a few small things. First of all, page number 2. As you could see, we're not at 10 o'clock, it's 8:30 and we changed the room, so it's a minor detail. And 2 more things to highlight here. On paper number 8, page 215 in the printed version, table 1, it should be set discharging MOSFETs TG and TP. So it's set TS in the printed version, it should be TG. And on pages 219 to 223, so figures 5 to 9, the word battery module is more appropriate than battery pack. Right. Let's start with the presentation. Today's presentation is structured as follows. I will start with an introduction and our motivation of conducting this work. We'll have a brief look at machines and batteries. We'll introduce low voltage high current drivetrains. And we will have a look at the first and second prototype machine that we built throughout this work. And they are low voltage, low power proof of concept machines. So these ones can't be used in an application right now. Towards the way towards 48 volt machines, we specifically look at some key components required, which is in-conductor cooling, a possible controller, and a reconfigurable battery. And finally, I will summarize my talk. According to a recent study, air pollution causes 5.5 million deaths a year. So if we look at the picture here on the top left, smog in China, here in this case, or in India, but this is a worldwide issue. So if we look at the picture from the ESA Sentinel-5 satellite showing the NO2 emissions in southern and central Europe, we see a large concentration here at the big city and industrial areas. NO2 is a product from combustion of fossil fuels, so we may assume that a large portion here is from transportation and personal transportation. And due to the still ongoing pandemic situation where lockdowns have been involved, we should see a reduction then of these levels. And indeed, if we look at the same time frame 1 year later, March to April 2020, we see a huge reduction of NO2 emissions. So as we see, transportation, especially personal transportation, has a large influence on basically global warming also. So the question is now, how could future mobility look like? To my point of view, we will see a lot of battery electric vehicles, at least for short distance and city driving. This is a great choice. While these cars don't have any local emissions while driving, they still need to be recharged, and electricity is required for that. And the electricity itself also needs to be produced, and then it highly depends on the power source used here. If coal is used, it has a very high environmental impact. If we use hydropower or solar power, so PV installations, it has very little environmental impact. And also prices involved here. Where in Germany a kilowatt hour is about 3 Swedish crowns, while up here in the north it's about 1 crown. So sometimes these days it still could make sense to drive a diesel car if you just look from the economical perspective. So that's why I think we will see large PV installations that will support charging these cars as a very cheap and clean power source. And what we see here on a big shopping center, large solar installation, that actually would also work at your home. Right, let's have a look at BEVs used today, battery electric vehicles. What do they have in common? Well, the electrical traction motor and the traction battery for sure. But there's something more they have in common. It's the voltage level that you're using. So these cars shown here, they're in the 400 volt class. That means this is high voltage, that's dangerous, and it requires authorized service personnel. And in case of an accident, valuable time might get lost to ensure that the high voltage source is safely disconnected. And even a fully discharged battery might have lethal voltage on its terminal. That also comes into account when we talk about recycling of these batteries. There's a trend going to even higher voltages, 800 volt systems. To my knowledge, the first production car with an 800 volt system is the Koenigsegg Regera, which is a smaller company in southern Sweden. This is these pretty special cars, the so-called supercars. And the car here is a hybrid one. It has 3 electrical engines together with 525 kilowatt, and they use it for torque filling, torque vectoring. And thus they have a very small battery with 4.5 kilowatt hours. Pretty lightweight, 75 kilogram, is liquid cooled, has 192 cells in series and just 2 in parallel. And to my knowledge, the first BEV, battery electric vehicle with an 800 volt system, is the Porsche Taycan. And this year, Kia and Hyundai announced also cars with the 800 volt system that should be launched to the market. So we see a trend to even higher voltage levels on BEVs. Let's have a look at machines and batteries, specifically some common properties of electrical machines. The major part of the losses of an electrical machine are resistive stator losses. What we could see here is an example of a squirrel cage industrial induction machine. And even at 160 kilowatt, the resistive losses is the largest single loss share in the machine. Among the most common electrical failure is the stator winding inter-turn fault. That's what we see here in the picture. So it might start as a short between 2 adjacent wires or a short to the stator slot, and finally propagates in the coil and ultimately destroys the electrical machine. Machines with a random wound winding have a typical very low copper fill factor of 0.4 to 0.5. Here on the right side in the figure we see the wires with the isolation coating. It's usually 2 layers of paint, and epoxy resin filling the void to increase the thermal conductivity and mechanical stability. Speaking about thermal conductivity, if we have many slots in a wire, the design needs to account for that, and the hotspot is usually in the center of the coil, and the heat needs to be transferred to the stator to be finally extracted from the machine. So heat transfer on this winding type is limited. And if we have high power machines, they usually require high voltage. In industry, having high power machines with 1000 volt and more is common practice. Here's another example of loss share of a squirrel cage induction machine. What I'd like to highlight here is that there's effort being driven to reduce the machine's losses. But as we could see, this purple color, which is the stator resistive losses, is roughly the same. And they are still there even in case 4 and 5, which is the synchronous technology, which is these days often used for EVs. So even EV machines have a large share of the losses, if not the largest, is the resistive stator losses. Now I'd like to show you some design rules for machines that have been applied since more than a century. Pretty common here, P equals I square R. So meaning if you would like to reduce the resistive losses in the machine, you would aim for a low current, which in that turn means you need to increase the machine's voltage to maintain the power level. However, on the machine itself, if you'd like to create an air gap MMF of a certain strength, it doesn't matter for the machine if you do that with a single coil and 100 ampere, or if you take 1 ampere and take a coil with 100 turns. So physics of electromagnetism tells us that it doesn't matter if the slot current is generated through a single conductor or many turns. But what is always done here with this law is that we try to increase the voltage to reduce the current. But this is not necessarily the best case to reduce the losses because of the things I've already mentioned before. Let's have a look at the batteries of EVs. What do we expect from them? They should be affordable, meaning have a good price to performance ratio. We expect a long lifetime. We don't want to replace these things after 2 years. And we would like to be that they are environmental friendly. We'd like to have comfort, which means high energy density devices to provide long range. And they should be kind of fun to drive, which requires high power density for decent acceleration and recupation. And we expect that they could deliver and do recupation in seconds. The bad news is we're not there yet. What we see here is a Lagoon plot showing the specific energy density at cell level here, and this is the specific power density at cell level. EV batteries used these days, they already reached a power level of 260 watt-hours per kilogram. And this is very high energy density cells. And as we see here, if we like to have high power density, this is usually an excluding factor. What I get from Tesla's last battery days, that they're working on a cell technology that should be able to combine both. That would mean we are somewhere in this range, for example. Also like to highlight here the supercapacitors, the green curve here on the left. They have a very low specific energy density, but a very high specific power density. And these ones could be used for the short-term cycling, recupation and deceleration of the car, and may be used or could be used actually to increase the battery's lifetime. I'd like to summarize my introduction now. The main machine losses are resistive stator losses, and the most common electrical failure is the stator interturn fault. Machines usually have a low copper fill factor. However, in case of hairpin winding technology that's also used in EV machines, the fill factor is of course higher. On the battery side, it's very complex, expensive, and has right now still a high environmental impact. And a considerable monitoring and balancing effort is required for these high voltage batteries. We usually talk about 96 to 192 cell stacks, meaning voltage levels that need to be monitored and balanced. This is a rough number. For example, Volkswagen's ID.3, their electric car, has in one battery configuration, I think, 112. So it gives you a rough orientation that's somewhere in between 100 and 200 voltages that need to be monitored and balanced. High voltage is a safety risk for passengers in case of an accident, for rescuing personnel, for the maintenance person in the workshop, and last but not least, when you like to recycle the battery. So even a fully discharged battery might have a lethal voltage applied to its terminals, or when you open it, it's accessible inside. So a considerable isolation effort is required. Battery cells itself, they're low voltage in nature. That's due to the chemistry used. So a considerable effort is required to create high voltage with this low voltage technology. And if we look back, a century ago, before the age of internal combustion engines, we already used EVs, and they were low voltage in nature. So the question is now, if we always need to use high voltage, or if maybe the low voltage technology is better. So let's have a look at the advantages of a low voltage drivetrain. We have minimal isolation effort, and we can use structural parts as conductor. They are safe to touch by design, and low voltage MOSFETs with a very good price to performance ratio can be used. If we talk about automotive 48 volt, the standard VDA 320, that would mean we need to use 80 volt switches to handle the dynamic overvoltage range. Redundant multi-phase single-turn windings are used, so we have increased redundancy in the machine. And we have a resistive loss reduction by a copper fill factor approaching 1. We can use in-conductor cooling, which increases the current density of the machine. And we have a reduction of the battery pack's complexity. It's a factor of 8 less series connected cells if we talk about a 400 volt class, or factor of 16 compared to an 800 volt class high voltage drivetrain. This work mainly focuses on the construction of a high current low voltage prototype, which is a low power proof of concept machine. In order to get there, we basically needed to reverse all common design principles. This is an overview of a possible low voltage drivetrain. We have the low voltage high current machine here on the right side, and directly attached is a MOSFET based drive electronic. In our case, that machine will be fed from a lithium-ion battery that is reconfigurable. So in driving mode, we have a 48 volt applied. Christine? And in charging mode, we switch it over to a high voltage. These parts are included in this thesis here. What's not included is the high voltage fast charging, low voltage charging, and possible low voltage supercapacitors. Just hide this. There we go. So this is our progression towards the 48 volt low voltage drivetrain. We started with the first prototype machine. That's investigated in paper 2, and the air gap flux density measurement setup is described in paper 1. Paper 3, we did the characterization of the machine and finally found that the resistive losses are fairly too high. So, however, the design looked promising, the switches were not the limiting factor, so we decided to build a second prototype machine. That's described in paper 4, and while we did the measurements for paper 4, we figured that we cannot measure at the highest speed, highest current range, and that was partly due to the machine's armature action, which is investigated in paper 5. Now, knowing that the machine's technology is working, the switches are not the limiting factor, we decided to look at key components for a 48 volt drivetrain. A possible controller is discussed in paper 6, paper 7 focuses on machine cooling, and paper 8, which is still work in progress, is a reconfigurable battery. Right, so let's have a look at the first prototype machine. The mechanical construction is shown here on the left side. This is the cross-sectional view of the machine. This machine is a 2-pole permanent magnet machine in an outrunner configuration. And the reason for an outrunner configuration is more like a historical one. Initially we thought this should be for another application, but when we finally came up with this idea of application for EVs, that turns out to be not the smartest choice, so the 48-volt machine will be a classical in-runner configuration. We have 22 magnets here, 7 mm long, 70 mm long. The outer diameter measures 160 mm, the inner one roughly 91, and we use classical electrical steel. I'd like to highlight the low copper fill factor of this machine, and this is due to the use of stranded wire coils for the first prototype machine. What we see here is the measured air gap flux density of the machine, and sensor 1 in red and sensor 8 in blue, they have the lowest air gap flux density, and this is because we measure the end effects of the magnet, and the black curve here is the FEM simulation, and a good match there was found. What we see here is the integrated power electronics. Due to the limiting space on the inner stator, we have divided it into two PCBs. It's the MOSFET board here on the left side and the controller board on the right side. These two PCBs get stacked together, and we have then two parallel IRF. These days it's Infineon 25-volt CAN-type MOSFETs, and that deliver a phase resistance of 1/4 milliohm. We have 13 individual phases on this board. Each one can handle more than 120 amp. The switches used here, they're already discontinued, and the current generation is already 40 volt and would lead to a phase resistance of 0.17 milliohm. And that are basically drop-in replacements. Now I'd like to show the machine's winding layout and commutation pattern. So what we see here is the block diagram of the machine with the 13 coils, and here the adjacent phases on the power electronics. Here on the left side is the machine with the 13 coils. We use N-channel MOSFETs for ground switching. The reason is for that is that this simplifies the power electronics, however limits us to unidirectional current flow. On the power electronic side, we have 4 times less phase resistance compared to a half-bridge configuration. The reason is that we use 2 switches in parallel, while a half-bridge configuration would be 2 switches in series. This also means we could only use 5 of 13 coils to be powered simultaneously. If we look at the machine's winding here, they are 180-degree shifted, so it's a full pitch winding, and we have 13 individual of them. If we now draw in the magnets there, the solid color is where we have highest air gap flux density, and the light color is the transition region from 0 to full flux density. The blue here is the active commutation window of the machine, so it's the 5 red marked active coils, and the orange color is the step width, the commutation step width. So what we could also see is that it's theoretically possible to run on 6 of 13 coils. However, that would mean we need to reduce the commutation step width to half. And another thing is, if we run at high speed and high machine load, we had increased jitter on the position detection, so we decided to go with 5 coils for both machines throughout all measurements to be on the safe side. Right, what we see here is the first time when we had the machine assembled together, still very long flexible cables here and a very thin connection ring, but as said, this is the first time when we had it together. So if we do the resistance measurements on that, we see that we have a mean stator loop resistance of 1.6 milliohm and a quite large resistance variance here. So we changed the connection to a machined ring here, shortened the stranded wire coils, and tried to get a low resistance connection here. The result of that effort is that we now have a mean stator loop resistance of 1.28 milliohm and much less resistance spread. I'd like to show you a short video of the first machine. As you see, it's still the first winding setup with the longer wires. What we're going to see is an acceleration to 2000 RPM with 180 amp. We can also hear that the machine vibrates quite much, so this is everything else than a perfect mechanical setup here. Now stator current is disabled, and this is the machine's EMF it generates right now, so it's a quasi-square wave. This is from the measurement, the maximum total losses we found. They were found to be 206 watt at 520 amp, 1500 RPM. And the maximum resistive or the resistive losses at that point, which is this plane here, they were found to be 170 watt. The winding resistors account for 70 watt, and the MOSFET losses down here, they're negligible with less than 10 watt. I'd like to summarize a bit the design of the first machine. We have a measured air gap flux density of 0.87 Tesla, the phase loop resistance, which is measured from the machine's terminal to terminal with one active coil, is about 3 milliohm. And since we run 5 in parallel at all times, the terminal to terminal resistance is 0.6 milliohm. And the machine was found to be operatable at continuous drive currents of 400 amp. To conclude on the first machine, resistive losses is 83% of the total machine losses, so fairly too much. MOSFET losses is negligible, resistive winding losses are 42%, and various contact losses more than 50%. The highest efficiency was close to the no-load condition. As improvements for the next prototype, we drastically need to reduce the resistive losses and coil on connections, and we need to improve the mechanical design and magnetic design. As we heard in the video, machine was vibrating quite much, and we had some hassle during assembling it. So let's have a look at the improved second prototype machine. Mechanically, it's nearly the same as the first version. However, magnets are a little bit longer, so the active machine's length has been increased by 29%. Magnetic material usage has been reduced by 20%, and we still have an increased air gap flux density. The biggest change is on the electrical connections. We use machine copper parts in the machine for all high current paths now, and the copper fill factor has nearly doubled, reaching 0.84 now. And that was achieved using solid preformed coils. Let's have a look at them. This is one of the 13 identical coils, and here doing assembly process in the inner stator of the machine. So what we see here is the machine's end winding during the assembly process with the steel sheets. This is the render of the machine, and the end winding that we had in the top view is at the end here. Here we see the power electronic with the MOSFET board here, the controller board on top, and these are the machined connection parts. The outer one is the VCC ring and the inner one is the ground ring. What we also see is the machine's support bearing that was required to measure it on a straight shaft configuration. We'll see that later. I'd like to show you a second short video of the second prototype machine on our in-house test stand. And this is an acceleration with 500 amp to 750 RPM. We see here about 500 amp and 0.73 volt at 750 RPM. So temperature is quite low with forced air cooling, that's not an issue. And here in the back we see the machine's EMF during motoring mode. Right, once we were sure that the machine is running, we packed it up, shipped it to Munich and put it on a calibrated test stand. So here we see our prototype machine, the support bearing required to have this outrunner machine in a straight shaft configuration on the test stand, and the classical torque transducer and the DC load machine here on the right side. So we used forced air cooling, up to 600 amp of continuous drive currents has been tested, and up to 3000 RPM. And the results I will show now is from the data collection during 30 hours. What we see here is the second prototype's resistive loss distribution. We see here the phase resistance of 1/4 milliohm, the switch resistance there. This is coil and VCC terminal ring is about 0.6 milliohm, and the remaining losses are on PCB and contact losses about 0.3 milliohm. That means we get now a mean resistance including power electronics of 1.14 milliohm. For the prototype 1, this was 1.28 just for the coil. And since we have 5 active coils at the same time, they're in parallel, the machine's terminal to terminal resistance is below 1/4 milliohm. So we can say it's better than a short. What we see here is the torque speed efficiency map of the machine, including the support bearing. Since we didn't have any, let's say, calibration data we trust for the support bearing, we decided to publish all results, including the support bearing. So the real machine's performance was actually a bit better than reported here. So we reached 83% here at that plane, which is at 2000 RPM and 400 ampere. Let's have a look at the machines and resistive losses. The total machine losses, they scale with the machine's speed, and the resistive losses, they scale with the current, which is the torque here. And as you see here is a little patch missing, which is the highest current, highest speed range. The reason for that is partly the armature reaction of the machine. We'll discuss that shortly. Let's have a look at the resistive loss share. Here's the plane again from before. 94 watt at 600 amp, the maximum total resistive losses. Winding losses about 50 watt, and the MOSFET losses, they are still negligible below 21 watt. So also for this machine, the switches are not the limiting factor. This is the machine's armature reaction. So as I said, during the measurements we found that we really suffer from the armature reaction, so we did a FEM simulation on that, and the blue curve here shows the air gap flux density, which also is basically then the EMF voltage of the machine. In blue is the quasi-square wave is unloaded, and the highest data current we have in the machine, the more distorted does the EMF get. As consequence, for our machine, since we use concentrated coils, and they by nature suffer more from the armature reaction than distributed windings, we have a current shift in our parallel connected coils. That means for our machine, we get peak currents at the two last phases and coils in our commutation window. So that means the next generation needs phase current control to compensate for that. Here's an example of the armature reaction of the machine looks like at 750 RPM. What we see here is a 500 amp total stator current, the red curve here on top, and this is the machine's single coil or phase current. This is without current control, so we see an increase at the fourth and fifth phase, especially at the fifth phase, reaching a 150 amp peak current. If we add pulse width modulation, superimpose it to the fourth and fifth phase, we see a current reduction here and an increase in the remaining three coils. So that means the principle works for this type of machine. And the next machine's 48 volt machine will have phase current control. Right, if we compare the number 1 and number 2, both prototype machines, we see largely that we have a very much reduction of the phase loop resistance, more than 60%, from 3 milliohm down to 1.14, and the terminal-to-terminal resistance is now 0.23 milliohm. And this machine was possible to operate with continuous currents of at least 600 ampere. That's what we have tried. To conclude on the second prototype machine, we have a copper fill factor of 0.84, very low terminal-to-terminal resistance, and managed to run it with 600 ampere drive currents with forced air cooling continuously. MOSFET and PCB losses now account for 42%. The peak machine's efficiency, including its support bearing, was found to be 83%, and this efficiency is at about 70% torque speed range of the machine. Improvements for the next generation 48 volt, we now need to develop new power electronics with reduced resistance. That will be a half-bridge configuration with current control. And we will use non-magnetic position sensors. Right now we used Hall sensors, which worked fairly well for that application. However, we had increased jitter at the position detection at high speed and load conditions. Great. So let's have a look at in-conductor cooling now. This is a render of our current design stage of the 48 phase 48 volt machine. What we see here is a W-shaped coil in red, one of the 48, that is hollow and designed for cooling with ethylene glycol water. This conductor is 950 millimeter long, has a 1.5 millimeter inner diameter, which is the center hole here, 4.5 millimeter outer diameter. That brings us to an effective copper area of 14.14 square millimeter. We have a straight version and a W-shaped version. They're exactly identical It's just that one version is straight and this has been bended. If we measure with a pressure drop of 100 kilopascal, which is about 1 bar, we get 0.29 liter per minute flow rate for the bended version and 0.31 liter flow rate for the straight version of the conductor. And this conductor is designed for turbulent flow, which increases the heat transfer. This is the conductor during production and assembly process. Here we see it out of the bending machine. This is with ceramic insulation coating, and here is one of the coils inside the plastic mold. Here we see the assembled machines winding in the plastic mold. All 48 are in place. Power electronics will be hooked up here, and this is the machine's end winding here at the back. This is the experimental setup we have used for the measurements. Here we see the straight version of the conductor in place. This is inside this insulation coating and has temperature sensors attached along. What we do not see here is the coolant's inlet. It's hidden here behind the heatsink, and here the black hose is the coolant's outlet there. Here on the bottom is a lab chiller that was used to keep the coolant's inlet at the same temperature. On the right side is the flow diagram. Here's the lab chiller again. Then we have a booster pump to reach the 100 kilopascal of pressure drop we want, and we measure coolant's inlet and coolant's outlet temperature here. The conductor is clamped in massive copper clamps here that are cooled to reduce the heating effect from the feeding cables. These cables get quite warm at 500 amp, they reach about 70 degrees. And here as well. This is the results from the pressure drop versus flow rate. We did an analytical calculation for the turbulent flow in solid blue here, and for the laminar flow in solid red. The measured W-shaped conductor is here in purple, and a good match was found to the turbulent flow, and it has a little bit higher pressure drop or less flow rate. The reason for that is that we have the bends, so this was expected. A good match was found for the simulated conductor that is in between laminar and turbulent flow. However, for the yellow conductor, which is the measured straight conductor, it's a bit different. We can assume laminar flow at low flow rates, and we can assume turbulent flow at high flow rates. And in between, this is unstable. So we can assume that we have dynamic changeovers from laminar to turbulent. And that was confirmed by the temperature sensors we have on the conductor. So usually would assume a temperature gradient from the coolest to the hottest place. But sometimes we get a sudden change there, which is in the first 25 to 40–50% of the conductor. So we assume it's due to the design of the coolant inlet there. So this is something for the future work to investigate. Takeaway message here is that the W shape of the conductor helps us to ensure turbulent flow and thus to increase the heat transfer into the coolant. What we see here is temperature versus flow rate and current. So if we have about 21 to 22 degree coolant at the inlet, a pressure drop of 100 kilopascal, resulting in a flow rate slightly above 0.3 liters per minute. And then we ramped up the conductor current and measured the adjacent temperatures here. Here on the right is the simulation of the same conditions. What we could see here is at 520 amp, there's a good match of the coolant's outlet temperature to the simulated one, as well as for the conductor's temperature here. The reason why the measured values are a little bit higher is most likely from the massive copper clamps that we have and the heating from the feeding cables that they reach about 70 degrees C. So if we go a little bit further away from the clamps, it matches a bit better. All in all, we can say we have a good match between simulation and measurements here. The last one I like to show here for the conductor cooling is the temperature gradient. This is the 700 ampere simulation of the W-shaped conductor. We used 65 degree hot coolant, which is here, and we see a linear increase of the temperature. We can also see that we have an increased coolant mixing due to the bends here. And the result is that the W-shaped conductor helps us to increase turbulent flow. This simulation is a power dissipation of 710 watt was found, and a conductor temperature rise of below 57 degrees. And the flow rate required for that is slightly above 0.3 liters. And from this simulation, we have 50 ampere per square millimeter. Right, let's have a look at the possible controller. We call it a hybrid controller because it's a combination of a digital signal controller and a CPLD there. We have an isolated USB UART. This is to avoid ground loops, and we use terminal emulation that we do not have the requirement of a matching PC software there. The controller used is a DSPIC dual core, which is a IC from Microchip, and the speciality is the very low resolution of its PWM module with just 250 picoseconds. So with this setup we have up to 13 individual PWM pairs, 13 in total, and 7 of them could be used fully individual. And this was designed for converter prototyping and actually could be used to run the first and second prototype machine. When it comes to the next generation machine with 48 phases in half-bridge configuration, this is most likely too small. We would need a set of them, need to synchronize them, so most likely we need to go for an FPGA solution here for the next one. I shortly like to show the block diagram. What we see here is the DSC with its 2 cores. Slave core handles all the PWM generation and feedback. Then we have here the CPLD, responsible for synchronization, hardware protection, and is also used to create special PWM patterns. And the master core here is responsible for handling the user interface. Now let's have a look at the final paper, which is still work in progress, which is a reconfigurable battery. So fast charging of 48-volt batteries is a real challenge. We need to use the existing infrastructure, which is high voltage. Sure, we could use point-of-load converters, but that would add additional switching losses. So we have the idea of try to do a reconfigurable battery by adding basically MOSFET reconfiguration circuits to each module. So the battery shown here is for 48-volt discharging and recuperation, meaning during driving, and could be switched over for high voltage charging. An experimental setup we see here is 8 modules of lithium iron phosphate. That is a pretty stable chemistry, and that's simply to increase the safety. So this is simply much better to work with. It's not that dangerous. This is the schematic of our proof of concept setup. We see here the battery modules. The first module down here has no reconfiguration circuit, and the remaining 7 have the reconfiguration circuit on top. So in series configuration, we have this series MOSFET TS that will be closed, and in parallel configuration we have TG and TP that are the parallel MOSFETs. So the battery is always kept in 48-volt parallel configuration, and only if we go for charging we switch it over to high voltage series mode. The observation here is that the parallel switches need to be able to block high voltage. The reason for that is if we now grab module number 8 here and assume 400 volt at this connection, and we have always 48 at the red link and always ground 0 volt at the blue link. That means we need to block at least 350 volt here at TP and at least 400 volt here at TG. What we also observed is that we have high inrush currents, creating high voltage spikes here. So the actual reconfiguration circuit looks like that. We have added a high ohmic path here that is first enabled, and after that, after 20 microseconds, when the parasitic capacitance have been recharged or charged up, we enable the low ohmic switches here. And we also observed that it's a good idea to isolate the ground, so the control signals should have isolation. And that helps a lot to avoid to reduce the parasitic capacitance. So I'd like to show you 2 measurements of charging and discharging. What we see here is the high voltage charging with 450 volts. So the pack is in series configuration. That means we have equal module current and the module voltages may differ. We see that here, number 5 seems to reach top charge or has a high internal resistance. All in all, we can say works as expected. Let's have a look at 48 volt discharging. This is for 1 hour with 80 amps, so 8 modules in parallel, so 10 amp per module. And it means ideally we have equal voltages at each module and the module currents may differ. And the same applies if we do an acceleration test, meaning 10 seconds discharge at 200 amp for the pack, so 25 amp per module. And we can also say works as expected. So, now I'd like to summarize my talk. Low voltage high current drivetrains have many advantages. They are safe to touch in all cases, even in case of an accident, since no lethal voltage is created. The minimum isolation effort is required, and the multi-phase design increases redundancy. They provide highest copper fill factor due to the use of single-turn or half-turn windings, and we have reduced thermal resistance between stator and winding. There's a clear trend towards 48 volt drives with increased power rating. OEMs are already offering 30 kilowatt drives for integration, and Mulabo recently released a 48 volt 80 kilowatt drive for boats and has also shown a 110 kilowatt drive integrated in a car. This is supported by the rapid development of high current MOSFETs. They show increased current density, increased blocking voltages, and have a very good price to performance ratio, and that at a reducing cost. So to conclude my presentation, low voltage high current traction drives are definitely feasible these days, and high current MOSFETs are not the limiting factor towards low voltage high current drives. The low resistance design is required to support high current, and that can be done or is done by the use of large cross-sectional area conductors that support in-conductor direct cooling to also increase the power density. And the use of multi-phase design, which increases redundancy and reduces the individual phase current. So we have successfully demonstrated a pioneering machine design thought to be disadvantageous or perhaps impossible a decade ago. The key enabling component are today's cost-efficient high-current MOSFETs. However, 48 volt fast charging is a challenge, and maybe our reconfigurable battery might be a solution for that. So lessons learned for me is we absolutely underestimated the effort required to construct the prototype machines from scratch, and writing the controller's firmware was more time consuming than expected. Timing is really crucial. If you get this wrong, you replace a lot of MOSFETs, and don't try to implement USB on a single core controller. It's going to be a nightmare. For the future work, we need to scale up our drive to 48 volt. This is the current work in progress stage here. And there will be half-bridge power electronics used for that with current control, and we need to investigate high current PCBs. For example, here we did some tests with machine copper parts that basically get pushed into the PCB then. We also need to investigate if ethylene glycol water could be used as coolant for the low voltage machine, and we need to investigate the temperature gradient there to ensure that we have always turbulent flow on the winding. And we need to investigate our reconfigurable 48 volt battery and improve that a little bit. So I think the takeaway message from today's presentation is, where battery and drive are at very close distance, safety and redundancy is requested, low voltage might be the superior solution. And this also opens a new design choice for EVs. So we have the 800 volt on one end. To my personal point of view, there will be the megawatt range cars, super sports cars, luxury cars, and we have the 48 volt system on the other side. So and with this type of work, it really counts never give up. So otherwise, we would not have ended up here. So and this is the last slide for my presentation here. So high voltage has also its challenges. Directly a couple of weeks later, when Audi has its first BEV launched, it turned out that water can get into the high voltage charging port, make its way to the battery, and can potentially lead to a battery fire. Thank you.
Okay, thank you very much. There's not that many here. But then before we continue with the question, we take a short break. So we at 9:45 we continue. Then we do some rearrangement here in the room. So let's all be back in 7 minutes. Okay, thank you.